OK, so an important question comes up with something like a superscalar when you're executing multiple instructions at the same time is what happens when you fetch two instructions and you, let's say, one of those instructions takes an interrupt or an exception as it's going down the pipeline. So let's take an example here. Let's say we have a load and then a system call instruction. Now, both these instructions can effectively take interrupts or exceptions. The load can take something like a TLB miss or an alignment fault. The syscall instruction, by definition, is effectively making an interrupt occur. And one of the interesting questions here is this load word, which is going to go down the pipe. If we fetch these two at the same time, and they start marching down the pipe, so this is our pipeline diagram. We fetch at the same time. We decode at the same time. The load has to go to the A pipe, or the load has to go to the B pipe, so it ends up in B, and the syscall ends up in the A pipe. Well, what does this exactly mean if the load is in the B pipeline, but it takes an interrupt and it commits in order first? Well, actually, let's think about that even. Let's think of even a simpler question here. What if the load does not take any faults and the syscall takes a fault? Which happened first, A or B? OK, so which should happen first in program order? A load and then an instruction after a load. The load should happen first, because in program order we go sort of top to bottom. But the load is in our B pipe here. In our A pipe, we have a instruction which takes a interrupt. Well, so what happens here, right, is that the load should go down the pipe and complete. And in order not to deadlock, basically your decode logic is going to have to sort of either know about this, or very, very late in the pipe, you have to have what we're going to call a commit point, which we're going to be talking about later in today's lecture. And you have to make some rational decision here of which of these actually occurred in order. And you somehow have to track that going down the pipe. And then you have to make a decision of, oh, well, the A pipe actually just took an interrupt. But in program order, the B pipe is the first instruction going down the pipe. So at the end of the pipe there, you're going to have to make some logical decision and have to have a little bit of control logic to make sure that you're not going to, let's say, take an interrupt for the syscall, even though, and kill the load instruction before the syscall. So one thing you could do is actually have both of them go down the end of the pipe, not kill the load, let it commit, and have the syscall actually take the interrupt. And that's probably the highest performing thing you could do in this case. Lower performance things probably would be easier, but that's probably the highest performing thing you can do in this case. OK, so we sort of introduced this two-way superscalar, in-order superscalar. One thing we need to think about is we add a lot more places that data could be coming from if we have to forward data. So we now, instead of, when we had one pipeline, we could bypass data out of here, here, and there. So there's only 3 places. But now that we have 2 pipelines, you've effectively multiplied the places that you can bypass out of, and now you can have 6 places. So if you go sort of pull the steering logic off, and then make your multiplexers bigger here, which are you're doing your bypassing, you end up with 6 different locations that you have to choose between for each input operand. And this is a relatively short pipe. So as you start to grow this to bigger and bigger pipelines, either in depth or in width, and you want full bypassing, you're going to have more and more, much wider multiplexers here and a lot more data being bypassed. So this actually becomes a problem, and you need to start to think about this really hard. So what are some solutions to this? Well, one solution that people sometimes do is they don't have full bypassing. You can only bypass out of certain locations. That's one option. Another option, which we'll be talking about a little bit later today, is you can actually maybe not actually have this pipeline register. And if you start to think of having out-of-order processors, you can start to think of committing information back to the register file early. So this pipe here has nothing happening in this stage. Well, can we just shove it in the register file? On first appearance, that sounds great. you start to think about that a little bit more, and you can start to get worried here because you start to see write after write hazards actually start showing up as real problems then. Because if you issue an instruction here which writes to the same register, which happens at the end of this load operation, we'll say, then you could actually get out of order writing to the register file. So you need to be cognizant of that. Other approaches that people take to this is sometimes they will actually have what are called clustered superscalars. So clustered superscalar, they'll actually have, let's say, 4 pipelines, and they'll cluster them into 2 pipelines of 2 each. And you'll allow bypassing between 2 of the pipes and 2 of the other pipes. And if you do bypass between the 2 sets of clustered pipes, then it takes an extra cycle, or you have to do it through the register file or something like that. So there's other approaches there to try to mitigate the blow-up of this bypassing network. And you have to remember, in something like a 64-bit processor, each of these are 64-bit buses. Each one of these little wires here. So these things get pretty big pretty quick. So you have to worry about actually running these things around the chip, because all of a sudden you have hundreds and hundreds of 600 bits running over, 600 wires running up and over just for your bypass from this simple pipeline. And if we go wider, it's going to be much worse or longer. So one thing that people do a lot to handle this bypassing from a critical path perspective, because this takes a long time, or starts to take a long time, is you start to break the decode and the issue. So we're going to sort of get away from our 5-stage pipes now. Up until this point, we've been doing things that you've seen in the first Patterson and Hennessy book. And now we're going to start thinking about things that have longer pipelines. So one good thing to do is you can actually break the decode and the register file access into 2 separate stages in the pipe, effectively making a 6-stage pipeline now. And what do we put? Well, one thing we can do is actually just break the decode into its own pipe stage, and we can try to figure out structural hazards even in that pipe stage. And that's something that people sort of traditionally do. They'll do decode, and they'll also look to see if you're going to have a structural hazard, let's say on a write port of the register file at the ends of the pipe. And then in the issue stage, I for issue, you'll do the register file, and you'll probably swizzle or crossover or steer the instructions to and the operands to the correct location. And of course, you'll do this bypassing if you have lots of bypassing operands coming back. So to give a sort of a brief pipeline example here we have 2 cycles, and each that execute 2 instructions per cycle. And we can see now our pipeline has an extra I in here, which is just an extra front-end stage. Okay, so this has some negative aspects. Can anyone think of one of the negative aspects of putting extra pipeline stages in the front of our pipeline? Yes. So branches. If we know that the branch gets resolved in out of the first execute stage of the pipe, or in our 2 pipe here, it's out of A0, we've just increased the branch cost by 1. So now something that would have branched, or a branch mispredict penalty of, let's say, 2 cycles just became 3 cycles. And this can start hurting your performance. And this really starts to hurt your performance as you start to go wide. So let's take this instruction sequence here, where we have this extra issue stage out in front, and we have a branch in the first instruction we try to execute, and then we just have sort of the fall-through code here, which so we predict fall-through. We don't realize that the branch happens till A0, and at that point we can redirect and just sort of kill everything that we've already gone in flight. But look at all the things that have gone in flight already. We're sitting here, which means we've had 1, 2, 3 other stages, if you will, or 3 other cycles to go fetch instructions. So we fetched these, we decoded them, we spent a lot of power, we spent a lot of time, we spent a lot of fetch bandwidth doing this, and then we just kill it all and revector to the correct branch target. So in this example here, we've killed 7 instructions. So this can have a pretty negative impact on our clocks per instruction, if you will. So let's talk briefly about how to fix this. We're not going to fix this all today. We have a whole dedicated lecture to fixing this. But what could we possibly do to minimize the probability that there is all these dead cycles here, all these killed instructions going down our two-way pipe? Well, we can hopefully, if we're lucky, we can try to predict the destination with some accuracy and have a branch predictor which will figure out where the destination of the actual branch is with some high probability. And then instead of executing, let's say, op A here, which is a dead instruction, which is the incorrect branch target, we can try to fetch and try to execute the correct branch target. And we're going to have a whole talk, we're going to have a whole lecture on how to get your branch prediction accuracy up. So in modern day processors, they're somewhere around 98% accurate, give or take a little bit. I actually don't know what the state of the art is on this because they keep getting better and more complex branch predictors. But there's some pretty simple things you can do to sort of get you into the mid-80s range. And then to get from sort of the mid-80s range of branch prediction accuracy to the 90s, you have to sort of put a lot of effort and time into that. But we'll have a whole lecture later in the course about branch prediction, just dedicated to branch prediction. But I just want to motivate here that if you have a longer front end of your pipe, and we're going to look at some pipelines where there's even more front end stages than just fetch, decode, issue before the branch gets resolved. Whenever you add an extra pipe stage in the front, that's going to impact your performance. Because even if you have a high prediction accuracy, your prediction accuracy is not going to be 100%. And if you mispredict, you're just going to have dead instructions going down the pipe, and it's just going to be wasting time, energy, and utilization of the pipeline.